Hi everyone and welcome to my YouTube channel. In this video, we'll be discussing Chapter 4, Assorted Configurations. This chapter is one of the most important chapters in the EGMO book by Evan Chen. But at the same time, it's also one of the most challenging ones because it has many configurations and many theorems that, or let's say actually lemmas, that you need to both prove at the beginning, because you don't know this dilemmas yet, and then you need to memorize them as well. So Evan Chen here, he suggested that this chapter can be viewed in two ways, either as just a set of configurations that you need to memorize and recognize on contests, because these configurations will appear a lot in many geometry problems. So you need to memorize these configurations in your head, and when you're doing some problem, you're going to spot, wait a minute, this configuration, I already know it. So you immediately know all the properties in mind about this configuration. So right now you're more comfortable working with the question. So that's the first view. The second view is that we can look at these famous configurations as just some famous problems that are going to appear in many problems. So for example, you're doing some problem and then you keep simplifying the question until you get that you just need to prove something, which is just the thing that we're going to be discussing in this chapter. So they are just like sub problems of other geometry problems. Anyway, right now what we'll be doing is the second view, because right now we don't know these theorems and lemmas yet. So we want to derive them with our hands, and then of course you can memorize these configurations and use them in other geometry problems. Alright, so what are we waiting for? Let's get started. Before we get started with the chapter, I want to point out that it's very important that you know all the lemmas that we have discussed in the previous chapters. So any lemma that we discussed in the previous chapters, not only the ones that we discussed, but even the ones in the exercises part. So all of these should be right now in your mind, because we don't want to prove them, to take some additional time to prove these. So here I actually want to share with you this file in which I just compiled the lemmas that appeared in the first three chapters so far. Actually, I wrote this one when I was just preparing for Math Olympiad in my first year. So let's just go quickly over those. So here you have just the orthic triangle. Just make sure that you know any of these, all of these theorems. In case you forgot about one of them, then of course you can go to the chapter and just remember it again. So you have the orthic triangle, you have reflecting the orthocenter, that if you reflect it you will get a point on the circle. You have the incenter excenter lemma, the golden point, which is L, the midpoint of the arc. You have the Michael point of a triangle, and you have all of these, for of course three tangents. This one is when you have a circle, then you have three tangents that are famous. Anyway, I don't want to explain it right now. You have the right angles on the Incircle Chord. So these are the angle tracing chapter theorems. You have also the circles one, anything related to the incircle and excircle. Make sure that you're really comfortable with the incircle and excircle, because we want to handle these in this chapter as well. Yeah, I think most of these are about that. Okay, we also have the third chapter, lengths and ratios. You have the homothetic triangles. You also have the 9-point circle. Make sure to have that in mind. Euler line, CVNS, all of these. Make sure to have this one in your mind. We are going to actually use it. This one is very important. Okay, so I think that's it. We can right now get started. Alright, our first configuration is Simpson line. And if you remember, this one has already appeared in chapter 1. in the exercises part, which it was just like one problem that you need to prove. So we have the Simpson line. What was the Simpson line exactly? If you just have like a triangle ABC with the circumcircle, if you take a random point P on the circle, then if you drop the three projections like to BC, AC, and AB, and you got X, Y, Z, then guess what? These are just collinear. So that works for any point P on the circle. And actually the converse of the theorem is also true. So if you have some points and you drop three projections, then if they were collinear, then this point is actually on the circle of the triangle ABC. Okay, if you remember, like just a quick proof for this one. So we just need to show these 3 points are collinear. So that means you just need to show this angle is equal to this angle here. However, you have tons of cyclic quadrilaterals here you can use. So this angle here is just equal to this angle actually. And this angle here, like you can say, for example, it's equal to this one here. Okay. What next? Next, for example, you can say that it's enough to show that actually these angles are equal. This one and this one, if you can show these, then because they are complementary, then that will be enough. And these are actually like equal because that's a cyclic quad, right? If you look at the cyclic A, B, C, P, then this one here is just an exterior angle, and this one is just the opposite to its interior part. So they're equal. Alright, so right now we have shown that like the Simpson line exists, right? We have a line that joins all of these. So, okay, that's good. Now we want to move on, because that's not really the thing we're interested in right now. Right now what we want to do is the following. We want to extend this one here. Extend this one. Okay, let's just move it a bit here. Okay, let's say this point here is K. So we just extended Px till it hits the circle. Alright, so if this was K, what do we want to do right now? We want to draw AK. And you should be seeing something very nice here. Clearly, as you can see, this seems to be parallel to the Simpson line. So AK is parallel to the Simpson line, and that's exactly what we want to do. So right now we're interested in proving. Okay, one thing we want to do actually in this chapter, we want to be very organized, because like I want you to keep this video as a reference for you whenever like you want to like look at the proofs for these, like remember how we proved them. You can always return to this video if you want, or actually I actually recommend that you right now have your notebook with you and try just to organize, like write, let's say, a sketch for the proofs, so that it's very easy for you to remember during contests. Because one very sad thing about these configurations is that like not all of them are really famous, in the sense that you can just reference them. It's always safer to write the proofs for them when you are doing like any question in any contest. So yeah, so that's exactly what you want to do. So we want to like have a sketch of the proof so that you immediately remember the key points, and you're like it's very easy for you to find the proof. So we want to prove that AK is parallel to the Simpson line. Alright, how can we do that? Try like to always pause the video and like prove it yourself. Okay, so the idea here is we just want to go for an angle tracing. We want to show these two are parallel, so that means we can, for example, go for these angles, this one and this one. So how can we show that this angle is equal to this angle? Well, if you look at this one, again, due to the like you have the huge amount of cyclic quadrilaterals, you can always manipulate these ones. So for example, this one here, you can just move it to this one. So these two are equal. So right now we want to show this one is equal to this, but actually this is very clear because they both have the same arc, which is arc AP, right? Both of them have the same arc, on like the circumcircle. So yeah, that's it, we're done. So let me just remove those and write a sketch of the proof. So again, the idea was very simple. We just show that AKP, this angle, is equal to ACP, which is equal to YXP. And yeah, that's it. Okay, nice. Now actually, what we want to do is, we want to draw, like take the orthocenter of the triangle. So I think we can just draw an altitude here. Yeah, and probably the orthocenter is going to be somewhere. Okay, somewhere. Just draw this one here. Yeah, I think it should be here. So okay, that's the orthocenter here. And what I want to do is I just want to extend the altitude from above. So let's just go above here, extend the altitude, and we want to intersect it with the Simpson line. Yeah, probably something like this. So we want to define this point here. Let's call it point L. All right. Okay, so now if you look at the diagram, you can see something nice. Oh, sorry, actually I made a mistake here. That's not the Simpson line, my bad. Simpson line is this one here. Alright, so let's define this one as L actually. And now you can easily see that we have a parallelogram, right? Look at it. XK parallel to LA, and the Simpson line LX is parallel to AK. So right now we got a parallelogram. So let's just add that. So we can just say that ALXK is a parallelogram. Alright, we're done with the first part. Now what we want to do is, we want to reflect point K, this point K, over the side, over BC. So let's do that. So if you just reflect, we get some point, probably, yeah, I guess here. So this point is just, let's call it K prime. It's just the reflection of K over the side BC. And now what we want to do actually is to prove that this point K prime is nothing but the orthocenter of the triangle BPC. So we just draw this one here. So you want to show that this K prime is the orthocenter of this triangle. How can we do that? If you look at it, you already have one altitude. K prime lies on the altitude Px. So you might think that we want to prove it lies on another altitude. However, here comes the nice idea, which like we've discussed and we've used many times. That should be in your head right now. You have an altitude, you have a circumcircle, you have a reflection. What does this remind you? Exactly, it's the reflection of the orthocenter. So if you think about it, if you just have like a triangle, you drop an altitude till it hits the circle, then you reflect it. This point is just going to be the orthocenter, because we know that the orthocenter is the point on the altitude that if you reflect it over the side, you will get a point on the circle. So clearly this is a unique point that satisfies this. It's only the orthocenter. And hence actually we're already done. So just using this property, we're already done. We know that K prime is the orthocenter of the triangle BCP. So let's add that as well. So the second idea is K prime is the orthocenter of the triangle PBC. Very nice. Of course, the proof is just like here. I'm just going to write a sketch of the proof. So just like reflection of the orthocenter. You should just remember this, and you'll immediately spot it. Okay. Okay, now what we want to do is, let's call this one, by the way, h, and remember that this one here is an altitude, so this is 90. Now what do we want to do? We want to actually look at the diagram and also get another parallelogram. Can you catch it? Our diagram, our parallelogram is AH K prime P. This one. It's just another parallelogram. And of course, the reason is you already have these two are parallel. So how can we show it's a parallelogram? Well, we have two ideas, either to show that these two are parallel as well, or we can show that these two are equal. AH equals PK prime. Anyway, we're not going to do any of these because actually you already know this. This was one of the lemmas that was mentioned in the file that I just showed you. And let me just show you that one. So it was this one. If you have a cyclic quad ABCD and you take the triangle ABC and BCD and you took the two orthocenters X and Y, then you already have a parallelogram AXYD. And guess what? That's exactly our diagram here. You have you have the cyclic quad ABCP, and you have an orthocenter here, another orthocenter here. Then you already have, like this one is a parallelogram. So it's just an application of that theorem. Yeah, that's it. Of course, to prove this theorem, actually, I'll just give you a hint here. Just reflect H and K prime here, like over the side BC, and try to show that AP is parallel to this one. Just like try to deal with it in that sense. Okay. So right now we also have this. So let's also add it. So you can just say that AH K prime P is also whatever, like a parallelogram. Okay, here of course to prove this, just like want to add, I will just give a reference to that lemma because it's literally an application of that lemma. I think that lemma was it called here? 3.17. So just keep that in mind. Okay, we're done with that as well. Now what do we want to do? Now we want to show that we also have a third parallelogram. In fact, try to spot it. So the parallelogram is, let me just draw these. It's LH X P. Alright, so let's prove that this is a parallelogram. Of course, we already have that these two are perpendicular to BC, so they are parallel. So we either need to show these two are parallel, or they are equal, or these two are equal. Okay, since like these are not really related to the previous things we've been doing, so we just want to show that these two are equal. And guess what? To show these are equal, we can just use the previous parallelograms that we've been using, that we've already like proven. So for example, this AH here, we already have a parallelogram for it. So we said that previously, where was it? Yeah, AH K prime P. AH K prime P, yes. So that means this here is equal just to this. Very nice. Now we also know that this one here is equal to this one from the other parallelogram that we got before in 1, ALXK. So we know these two are equal, but guess what? This is equal to this from the reflection. So we have these two are equal, and hence we are done. They are indeed equal, and we got the parallelity. Very nice. So let's just go and write that result as well. So right now, result 3, LHXP is a parallelogram. And of course the proof is just, we already have two parallels. To show equality, we have this, and we have this one as well. This one, of course, to remind you, we got it from 1. This one we got it from the second result, and hence that completes the proof. Very nice. Okay, so right now, what do we get from this actually, from this fact? So let me just erase these. So since we got this parallelogram, we can now draw the diagonals. So as you can see, the first diagonal is just the Simpson line itself, and the other one is this one here. So let me draw it in blue. Of course, as you know, in any parallelogram, the two diagonals bisect each other, right? So what we're interested here is to look at this. The Simpson line bisects pH. Simpson line bisect pH. And that's it. That's actually the final result that we want to conclude in this configuration. Because this one actually is very, very simple. If you look, you just have a triangle ABC, a circle, some point and its Simpson line, and then you just have the orthocenter. If you join pH, then guess what? The Simpson line bisects pH. That's it. Unfortunately, in order to prove this result, then you need all of these like points in order to show that. And that's why we try to organize these as much as we can, so that you immediately don't waste time during the contest. You already just know the sketch for the proof, so you can immediately remember the key points. Just extend this one here, drop a projection, continue this projection, then reflect it again, and then you have 3 parallelograms to show. Of course, since you already know this result, that pH bisects, sorry, the Simpson line bisects pH, then you already know the big parallelogram. So it's only it's only important for you to spot the other 2, and these are actually very easy to notice. So yeah, that's it. Now our second configuration is the Excenters. Basically, we have Excenters and the Incenter as well. So here, what do we want to do? We just want to have a simple triangle ABC, and we have the 3 Excenters, IA, IB, and IC. And of course, we have the Incenter as well. Remember that we already know that A, I, and IA are collinear, because this is the internal angle bisector, right? Remember that I is the meeting point of the 3 angle bisectors, internal ones. IA is the meeting point of the internal angle bisector of A and the 2 external angle bisectors of B and C. Same thing for each one of these. So now, what we want to show is, first of all, we need to show that these are collinear, as you can see. And this is actually very simple, because this thing is the external angle bisector, and this thing is also the external angle bisector, so they are the same line, of course. Okay, that's nice. But the nice thing here is actually, we know this is the external angle bisector, and this is the internal angle bisector. And we already know that these 2 are always perpendicular, and hence we get this simple, nice perpendicularity. So this one is actually, this angle is 90. And guess what? The same way you can just get this one here and this one here. And this actually means that what does the triangle ABC represent for the big triangle IA, IB, IC? It's the orthic triangle, right? And what does I represent for the big triangle IA, IB, IC? It is the orthocenter, right? Exactly. And hence we have this nice duality between the orthocenters and excenters. So we have this nice duality. So if you have an eccentric triangle, if you just look at it here, the eccentric triangle is IA, IB, IC for the triangle ABC. If this is the eccentric triangle, then the triangle ABC represents the orthic triangle for the eccentric triangle. So we have this duality. We can start with the eccentric triangle, and you can go to the orthic triangle, right? Something like that. You should always have this in mind. So in some questions, they will define ABC first, and then they will tell you draw the eccentric triangle. All right. Sometimes they will tell you the opposite, you have a triangle, and they will define the orthic triangle. And you should know that this thing actually, these 2 diagrams are actually the same, right? So in some questions, they might just give you a triangle ABC and just drop altitudes like this. something like that. And you should immediately know that this actually is the smaller triangle that we were just working with. So this small orthic triangle, like what does ABC now represent for it? It represents its eccentric triangle, right? And you should know that H actually represents the incenter for this triangle, like which is the orthic triangle. So keep that in mind. That's very useful, like this duality, like of the concepts. And another thing actually to add here, if you remember, what was the midpoint of IB, and this midpoint here, and this midpoint? You should remember these, the midpoints of these three segments. These were the golden points, right? Like the centers, actually the midpoints of the arcs. So if you just draw the circle ABC, this will be the midpoints of the arcs. And we agreed to call these like the golden point because they have like nice properties. We have, first of all, it's the midpoint of the arc. We know that it lies on the perpendicular bisector of the side, like this is equal to this. And we also know that it represents the center of this circle, which is super nice, especially like just the superior, like this triangle here, I, B, and C. So yeah, keep that in mind. So that means you can actually have a similar idea here. Like if you just draw this triangle as well, it will be homothic triangle, right? Oh, sorry, like just something like this, and this, and this. It will be just the like a homothetic to this one, right? Of course, scale factor. Like if you start from I, you want to get the red one, you can just scale it like this, I and half, right? Exactly. So yeah, keep that in mind, because we also have these perpendicularities as well. Okay, so we have this nice duality, and yeah, now we can just continue. Alright, our third configuration is like the incircle basically, and we're still dealing with the incircle. Right now we'll discuss many configurations about the incircle and the excircle. So right now we just have a simple triangle ABC, as you can see, and we just draw the incircle here, and this is I, the incenter, D is the touch point, and we have also the excircle, IA, the excenter, and we have X is the touch point of the circle with the side BC. And what is point E? The idea is we just drew this thing here, like the diameter. If we draw this diameter, then we get point E. And as you can see, our goal is to show that A, E, X are collinear. So that will be very nice, because you will have a nice way to get X from D, right? Like you just draw the incircle, get point D, draw at the diameter like this, and then just join AE to hit BC at X. Very nice property, very useful. That's why like we like here it was called like the diameter of the incircle, because we have literally a diameter here. Okay, so how can we prove this? How can we really show that A, E, and X are collinear? If you try like to go for angles here, like there is not much we can do, because this point E is not that nice actually. And of course, how can you use the fact that this thing like is 90 or whatever, like the touch point? So what do we want to do here? The idea is actually not very complicated. If you look here at A, and of course we have this line here and this line, we have the incircle is tangent to both of them, right? And also the excircle is tangent to both of them. So that means we have a homothency, right, centered at A, that takes this one here, maps this incircle into the excircle. Again, what's this homothency? You can just say the homothency is centered at A that maps point I to point IA. So this circle will be mapped into a new circle, and the center will be the image of I, which is IA. And still, like these lines are the same because they pass through A, the center of homothency. So that means the new circle is centered at IA and is still tangent to this line and this line. But guess what? The only circle that satisfies this is the X circle. So yes, so we do have a homotopy centered at A that maps the incircle into the X circle. Now how can this help? How can this help here? So if you look at it, I will move to IA. If we can show that E will get mapped to X, then we'll be done. But how can we do this? Well, the idea is actually like simple. You can, for example, think about point D. Where does point D go? Point D should go into it's still on the line BC, right? The image of B and C. What's the image of point B and C? So before we know that this thing is the incircle of ABC, now this should be also the incircle of the new triangle A, B prime, C prime. So for example, if you just continue maybe the circle like this, maybe, then it will be something like this line will go map there, right? Go map there, and you can just continue this one here and that one here, something like that. So point D will just be here. This one will be B prime and C prime. Let's call this D prime actually. Alright, very nice. Because right now the X circle actually is the incircle of the new triangle. So that means I was mapped to IA. D was mapped to this point. X forms a diameter, so that means it will be DIA like this, right? But guess what? Because these two guys are parallel, that means this one here is perpendicular from the tangency. So that means if we just join it, it will be also perpendicular to this one. But the only point that satisfies IA, X is perpendicular, is the point X itself. Alright, so we're done with the proof. Actually, we want to present another proof here. If you want to avoid drawing everything like this big circle, you can just provide another proof as well with the same homotopy actually. How exactly? Let's see. So okay, this same homotopy that maps the incircle into the X circle, if you look at it, if we just draw this thing here like B prime C prime, which is just the parallel from E to BC, so these two are parallel. Okay, so what does E represent here? Or actually, what does the incircle represent for the triangle A, B prime, C prime? It represents the X circle, right? The X circle for it. But now, if we do a homotopy that maps B prime to B, it will map C prime to C. So this triangle AB prime C prime will go basically into the triangle ABC, and hence the X circle will be mapped to the X circle. And hence it's our the same homotopy that we're working with. And that means that point E will go, which is basically the touch point of the X circle with the side, it will also go to the touch point between the X circle and the side, which is X. So basically they are collinear. Yeah, probably the second proof is easier than the first one because you don't need to continue the diagram. However, you just need to draw this one here. Okay, anyway, both of them depend on the same homotopy, centered at A. So pick whatever you prefer. So yeah, that's it basically. Of course, here, the lemma was stated, just as we said, D is the diameter and AE will meet it at X. They told you that here, BD equals CX. BD equals CX. Remember, we already know that because in our previous lessons, we already concluded actually what exactly is this. We know exactly what was this. If you remember, we said that this is S minus B, and this is also S minus B. So yeah, these of course are equal. In fact, if you just take the midpoint here, M, then we also know that these two are equal. That's very obvious here because it's the midpoint here, and this equals this, so it's also the midpoint of dx. But guess what? This thing is also the midpoint, and hence you have this nice thing. You can just draw IM. If you just draw IM, oops, we just zoom in. Yeah, this will be also parallel, right? Parallel to this. And of course it's a midpoint segment, right? So IM is just half of EX as well. Alright, yeah, that's it. So here I just like basically the sketch of the proof is literally just remember homotety, centered at A. Maybe you can say mapping incircle to Excircle. Yeah, that should remind you of the whole proof. Okay, that's very nice. Now, in fact, you might be wondering, if we have this nice connection between D and X, like I can construct X starting from D. Just start from D, draw the diameter, then join AX. That's it. You get this one. Then how about the opposite? Can't we get D from X? Well, actually, yes, you can. And in fact, you can just copy literally the same idea. So we just want to do the symmetry here. We just want to start from X, draw the diameter. But of course here, since it's the X circle, so you're going to draw this diameter here. Something like this. Okay, of course, continue that. And then just join it. If you join it, hit it with BC, it will be the point actually you're looking at. So something like this. Yeah, so basically keep that in mind. We have also a duality between the incircle and excircle as well. So you can, whatever like you prove here, you also have it here. So keep that in mind. Of course, the idea is the same as the proof is literally the same. All right, our fourth configuration is we still, like as we said, dealing with the incircle. But right now what we want to do is we want just to draw the triangle ABC. And as you can see here, we have just the touch point D and the touch point X of the exterior one. So we have exterior, basically the excenter here, IA, and the excircle, of course. And what do we want to do here? Of course, we have already proven that if you have D and then like you draw the diameter as we said, then you take AE and it will hit BC at X. Nice. And also the previous thing that we just said, that if you do the opposite, which is draw this one here, this diameter, then take AY, it will hit BC at D, just like the duality that we talked about. But right now what we're interested in is drawing XI, and drawing IAD, this one, these two lines. In fact, these are going to be meeting at one point, and this point actually is the midpoint of the altitude AK. So now AK is the altitude. Keep that in mind here. So that's basically the lemma that we want to prove right now. Okay, so how exactly can we show this? What does the altitude have to do with the incircle here? Okay, if you look at the diagram, first of all, we just need to show that X, I, M are collinear. If we can show that, then probably we can do the same, like duality, to get I, A, D, and M. So right now our only goal is just to show X, I, and M are collinear. How can we do that? Well, since we have this altitude here, then probably it's wise to do this as well. Just draw ED, because we also get a perpendicular. So yeah, have this one here. And now I just want you to look at the diagram, and you should immediately spot the proof. So remember that this is equal to this, and hence if you look at big triangle AKX and the triangle EDX, we have I is the midpoint and M is the midpoint, and we have these two are parallel. So that means that XI is the median of this, but it's also the median of the bigger one, because these are similar, right? So yes, that means they are indeed collinear. In fact, you can just consider one homotety centered at X that maps D to K. It will also map E to A, and it will map this segment into this segment, and hence the midpoint I will go to the midpoint M. So yeah, that's it. And now to show the other one, I, A, and D, and M, we can literally do the same thing. Remember the duality. But here we just like need to zoom out, because now we need to do the like the same thing, but here we need to draw this, and now exactly literally the same thing. We know these are equal, and now we have like a, k, d, and we have dx, y. These two are similar, so that means like also a similarity here, or like just from a homotopy, but a negative homotopy. Will map k to x, it will also map a to y, and hence the midpoint m will go to the midpoint ia. And yeah, that's it. We have proven both ideas. So now, like, just the sketch of the proof is just literally maybe let's say homotopy. You can either say homotopy or similarity. They are literally the same thing here. So homotopy centered at x. Yeah, I'm mapping what? DE to KA. So DE to KA. That's for the first part. The other part is same, but the center now is D, and this should map XY to KA. And yeah, that's it. That means we're basically done. That proves this lemma as well. Alright, so now let's move on to another configuration, probably our final configuration about the incircle. Alright, our fifth configuration and the final one about the incircle is the following. So in this diagram, as you can see, we simply just have a simple triangle ABC. We have the incircle and the touch point as like D. In fact, we have the whole contact triangle. So we have D, E, and F. And we have I is the incenter. We have the midpoint here, like AM is basically the median. And what do? We simply draw DI, so it's kind of the diameter. But before we used to like extend it here and then take this, right, to get X there, the touch point of the X circle. But now no, we just like intersect it with EF, the chord of the circle. And guess what? A, X, and M are collinear. So basically the median, DI, and EF are all concurrent. So that's exactly what we need to prove right now. So yes, what can we do? So if you look at it, we have like DI and EF, they're meeting at X, and we need to show this is a median. One not very nice thing is that what does the median even do with this? Like A, X, and M, what does M have to do with the whole diagram here? Seems a bit odd. So one idea to make life easier here is, instead of dealing with this M, which is far from these guys here, one idea is to take this X here and draw a parallel to the side BC. So we have B prime, C prime. So this is parallel to BC. What's the idea? Why is this nicer than proving M is the midpoint? Because right now, because we have this parallelity, we can consider like a homotopy from A, taking this one to this one, or the opposite actually. Then that means we just have to show X is the midpoint of B prime, C prime. So instead of dealing with a new point M, we just work with the same point X. So right now, what do we want to do? It's just like to show this is equal to this, and we'll be done. Alright, how can we do that? First of all, of course, let's just remember that I is the incenter, and hence these are tangents. So we have just some 90 degrees stuff, right? So for example, this one here is 90. We have this one here is 90. And we have this one here is 90 as well. In fact, from the parallelity, we also know that this one here is 90. Alright, very nice. That's one thing. Okay, right now what's our goal? Our goal is to show, as we said, that X is the midpoint of B prime, C prime. In other words, this thing here is the perpendicular bisector, actually, of B prime, C prime. So in other words, our goal is to show that I lies on this perpendicular bisector, right, of B prime, C prime. Okay, how can you show that this I lies on the perpendicular bisector? Well, what does I even represent here? Of course, we know I is the incenter, right? But what does it represent to B prime, C prime, A? you look at it, of course, if we join AI, then we already know that this is an internal angle bisector. Hence, our goal is to show that I lies on the perpendicular bisector of B prime C prime. But that's our goal. We already know that it lies on the angle bisector of A. Now this should remind you of something we have mentioned many times before. We have a point that lies on the perpendicular bisector and the angle bisector. Then guess what? What's this point? It's the golden point, right? The midpoint of the arc. So that means we need to show that I lies on the circle, like A, B prime, C prime. If we can show that, then we're done. Like any two will give you the third for free, right? We discussed that in the first lesson when we defined like the golden point. That is the midpoint of the arc, basically. So that means that our only goal right now is just to show that I lies on that circle. In other words, show that maybe A, B prime, I, C prime is cyclic, or that just I lies on the circle, the circumcircle of that triangle. How can we do that? One thing here also to notice is that you have this 90 degree, 90 degree, 90 degree. We have projections, right, from I into these guys. Try just to look at this and try to notice something here. There is something that actually is very obvious and will immediately like solve the question. Can you catch it? So we have a projection from I to this, which is the side AB prime, and from I to the side B prime C prime, and from I to the side AC prime. And guess what? The three projections are collinear. We have this line. So guess what? This is Simpson line, right? This is Simpson line because we project from I to all the sides of the triangle, and we already know that they are collinear, and thus by the converse of Simpson line, we know that indeed I must lie on the circumcircle, and hence we're done. So we have these two, so we get the third, and of course if you get the third, then you know X is the midpoint, and hence M is the midpoint, and we're done. So let's just quickly sketch a proof for this. So first of all, we need just to define like B prime and C prime such that B prime C prime is parallel to BC, of course, like at X, like passing through X, I mean. And now you can actually immediately say by converse of Simpson line, a theorem, I lies on the circle AB prime C prime, but AI is the angle bisector. Or actually, let's just say that I like lies on the angle bisector of B prime A C prime. From this we know that I lies on the perpendicular bisector because it's just like the midpoint of the arc of B prime C prime, and hence X is the midpoint of B prime C prime, and hence M is the midpoint of BC, and we're done. We got our concurrency. So that means we have this nice concurrency, an Incircle concurrency. If you have a triangle ABC, then you know that EF, which is the chord, AM, which is the median, and ray DI, which is the diameter of the incircle, they are all like concurrent and like 1 point. All right. So right now that was our last configuration regarding the incircle. So now we're done with the incircle and the excircle, and we'll be moving to other configurations. Alright, so in this configuration, we'll be introducing the isogonal and isotomic conjugates. These are like new principles right now, but they are extremely important, and you will see them appearing in many like geometry problems. So what exactly is the isogonal conjugate? So the idea is, let's just have a look at the diagram. If you just have a triangle ABC and you have a point P, just some random point P, then we have point P asterisk here that satisfies the following properties. This angle here is equal to this angle here. So you can say that they basically like AP is the reflection of AP asterisk over the angle bisector, right? If you just draw the angle bisector here, then this angle here is equal to this. All right, same thing actually for this one here. So we also know this is equal to this, and we also know that this is equal to this. So basically it just tells us that there exists such a point that has these three angles equal to the like opposite three angles, and we call such point, we call it the isogonal conjugate of the point P. Of course, you can easily see that if P asterisk was the isogonal conjugate of P, then P is also the isogonal conjugate of the other one, right? So we have a duality here. Okay, however, first of all, we need to prove that such a point exists. So how can we do that? Actually, the idea is really simple. We just have a point P, and we know that we have these three CVNs, like meeting at one point P. So we also want to define like another three lines, three CVNs, and we want to show that they are concurrent. So we're just defining them using the angles. And hence, if you want to show three CVNs are concurrent at a point, then of course, what better than Siva itself, right? Siva's theorem. So what do we want to do? The standard Siva or the trig Siva? Of course, the trig Siva here, because we have the angles. And as you can see, this is very like simple, because if you just apply trig Siva here, you will see that like sine this over sine this is the same as sine this over sine this. But because these, like when you take their pi, the product, they will cancel, that means also these should cancel. So yeah, that's it simply. So I will just say that the proof here is just like trig Siva. However, it's very important for you to prove it in this way, like define the lines using the angles and then apply trig Siva. Yeah, in this way. Anyway, like these are really famous, so you can actually comment these, like just say by isogonal conjugate, or like just immediately define it, because it's very well known. So you can say let this point be the isogonal conjugate of this one. But anyway, you know the proof, it's just like trig Siva, simple. In fact, this one is very important. But actually, before we discuss anything, let's just think of some nice examples. So are you familiar with any center of a triangle or two centers of a triangle that one of them is the isogonal conjugate of the other? Think about it. We do have actually, and we have done them actually in lesson 1. We have the orthocenter and the circumcenter, right? These are isogonal conjugates, because if you remember back then we just did this, like if this was H and this was O, then you can just do the angle tracing. This angle here is just like drop the altitude, 90 minus B, 90 minus B. And this one here, like to get it, you can just go for this one, which is 2B. And then because these are equal, then this one is just 90 minus B. Yeah, and back then we said this is like, this was a very nice reflection. Okay, so we just got the isogonal conjugate idea for O and H. Later on, we'll also see like G and another point, which is the Symmedian point. They are also like isogonal conjugates. But anyway, like the Symmedian point, we have not defined it yet. We'll be defining this in the next like configuration. Right now, what we're interested in is looking at this isogonal ratios theorem. This is very nice because it lets you go from angles into like ratios here. So what's the idea? The idea is we want just to take one line AD and we take the isogonal to this, the isogonal to this line. The line is isogonal to it. Let's say it meets the side at E. Then we actually have this nice thing. BD over DC times BE over EC is equal to AB over AC all squared. So let's try to prove this. Of course, this should be familiar to you. You should be able to prove it in a very easy way, because we're familiar with getting something like these ratios by using the ratio lemma. So we can just apply ratio lemma here. We can say BD over DC is just equal to BA, let's say like AB over AC, times sine BAD over sine CAD, right? We can also do the same thing for BE. BE over EC is equal to AB over AC times sine BAE over sine EAC. Well, guess what? Now if you just multiply these, we will get this squared, and these will cancel. Why they will cancel? Because of course we have BAD is equal to EAC, right? And CAD is equal, like this will cancel with these. So yeah, just by ratio lemma and the product, you will just be done. And this one is very, very nice, because as we said, now just if you want to get that this you want to prove that this angle equals this angle, then you just need to show some ratios, which is very nice. So this is regarding the isogonal conjugate. We also have another conjugate that is called the isotomic conjugate. It's not as famous as the previous one, but it's also it might come in handy. So let's just define it. So the idea here is very similar, but instead of equal angles, we have now equal sides, or equal lengths, sorry. So let's say something like this. This will just take another point, kind of reflecting now over the midpoint. So we take something like this point here, such that these two are equal. And we have the same thing. If we of course, let the point maybe be here. Take this one here. So if this was P, then we want to do the same thing. Maybe something like here, maybe. So that these two are equal. Then this one actually is the isotomic conjugate of the other one. So if this was P, then this will be, let's say, P asterisk. And of course, then we have the third relation as well. So if you just join the third one, they'll also meet. Actually, sorry, I think I screwed up here. Wait. It should be actually this one here. Sorry for that. Because this one here has this one here, while this one here was for this one here. Yes. So yeah, this one here, and that makes more sense, because we want now to draw this one here and this one here, and we want them to be equal. So you want these to be equal, and that makes sense now. Okay. Yeah, of course, something like this. Okay, again, how to prove that? Well, using the same idea. Again, we can just turn it into Siva, because we can just define P and the concurrency of three Sivians. Then we define them using the using the lengths. And now we just apply standard Siva, and as you can see, this over this, the product of it will be 1 by Siva. And now if we can just show that the same happens for the other one, but it does actually, because this by this over this is just the reciprocal of the previous one. So since the first one cancels, then the other one cancels as well. So yeah, just standard Siva will do both. So isogonal conjugate and the isotomic conjugate. Alright, so yeah, these are regarding the isotomic conjugates and the isogonal conjugates. And now let's move on to the next configuration. So now we'll introduce the Symmedians. What is a Symmedian first? Well, the definition is based on the isogonal conjugate that we just introduced in the previous configuration. So the idea is very simple. We just have a triangle ABC and we have a median. So AM is the median, M is the midpoint. So we define the A symmedian to be the line isogonal to AM. So it's basically the isogonal to the median, the line isogonal to the median. And of course, like we have an A median and we also have an A symmedian. In the same way, like we have a B symmedian and we have a C symmedian. And guess what? Just from the previous configuration, we know that like the three symmedians have a concurrency point, and this concurrency point we call it the symmedian point. And actually, we know exactly what's the symmedian point. It is the isogonal conjugate of what point? Exactly, of the centroid G, right? So yeah, so the symmedian point is the isogonal conjugate of the centroid. And yes, all of this is just based on the previous like isogonal like concurrency that we just proved. So it's just based on isogonal conjugate. And of course, like symmedian point, let's write it here. Is the isogonal conjugate of the centroid. Just this one there. All right. So yeah, that's like literally the definition. But now, why do we even care about these symmedians? Like, why do we want to reflect this over the angle bisector and get these lines? Basically, you will see actually that these symmedians appear a lot in the Math Olympiad geometry problems, and that will be fantastic if we can just catch these symmedians and try to analyze them and like get as many properties as possible, so that when you have the symmedians appearing in your like contest, then you immediately know what to do. Like, you're really comfortable and you know how to construct, what to construct, and what properties you have. So yeah, let's have a look. So the first lemma we want to introduce is constructing the symmedian. So here is a very nice way to look at the symmedian in another way. Like, beside from just reflecting AM over the angle bisector, there is another nice way, which is just if you have a triangle ABC and you have the circumcircle, then guess what? Just take the tangent here and the tangent here and intersect them at X, and take M as the midpoint of BC. Oh, sorry, actually, forget about what I said. Just like take the two tangents. Then guess what? Just AX is literally the A symmedian. So you don't even have to draw M. Just like once you draw these two tangents, then X lies on this symmedian, the A symmedian. So yeah, that's it. Of course, right now we want to prove that. So our goal is to like start from here, and of course show that to show this is a symmedian, we need just to show that this angle equals this angle, because that was literally the definition of the symmedian. It's just the line isogonal to the median. So if we can just show these two angles are equal, then we'll be done. But how can we show that? How can we get these like involved? What we want to do here is actually do like a phantom point. So we want to define this X first, because if you look at it, this X we're quite familiar with. We have many properties. For example, we know these two are equal. If you trace some angles, like, do you know what's this angle, what's this angle? Of course we know. These are all A, right? A as well. This one is B, this one is C. So like, we literally have nearly all the angles. So what we want to do, we want to start from X and then define M prime to be the line isogonal to this line. And our goal is to show that this M is the midpoint. So let's just call this one M prime. And as we said again, M prime is what? It is the isogonal, like AM prime is the isogonal line to AX. And our goal is to show M prime is the midpoint. So yeah, that's what you want to do. So let's here just first of all define M prime. So it's just a point on BC such that A M prime is isogonal to AX. And now we aim to show BM prime equals CM prime. Of course, to show that these two are equal, we can simply show that BM prime over M prime C is just 1. And hence we can use the ratio lemma. So let's just do that. So BM prime over M prime C, we can use the ratio lemma, and hence we can say it's AB over AC times sine BAM prime over sine CAM prime. But now guess what? Of course our goal is to get rid of M prime. Can we do that? Well, here we don't need M basically, but here we still need it because of the angles. But because we have the isogonality here, that means we can replace the angles. We can manipulate on the angles. So for example, the angle BAM prime, this one here, is just equal to this angle. So we can replace it with an angle that has X in it, and the other one as well. So right now we can just do this nice manipulation. So we can just keep AB over AC and just now replace the angles with the X. So BAM prime is now CAX, and CAM prime is now, yeah, we already have the blue one, it's just BAX. So that's very nice. Now we deleted point M prime, and now we can just work with X, and guess what, we know nearly all the angles, and we have some signs, so probably it's just now a matter of applying the law of sines. But where exactly? Well, clearly we have to deal with this angle here, this one here, and this big one. So for sure we're going to apply the law of sines on ABX and on ACX, so that we just get rid of these signs. Okay, if you think about it, to apply the law of sines, you need to choose like what sides, like AC and CX or AC and AX, or what exactly. Since we have this sign, then clearly we're picking CX because it's opposite to it, so we have to pick it. But another one we can pick is just AX because it's going to be like appearing in both of them, so it will cancel, right? And guess what, we already know that the angle opposite to it is C plus A, which is 180 minus B, so it's just sine B. Here the same thing. So yeah, that means we can just immediately do that. So I can just now apply the sine law. Actually, let me just write it here to have more space. So AB over AC is still there, but now sine CAX, let's just apply it actually here. So first of all, I can say that sine BAX is just going to be what? Yeah, it's going just to be BX times sine C. As we said, this angle here is 180 minus C, so I can just replace it with C because its sine of the supplementary is the same, right? So over AX, we just write it here. Oops. Over AX, it's just like a simple application of this law of sine. So here we just apply the law of sines in the triangle ABX. And now I also can do the same in the other one. So now sine CAX is just equal to CX again times sine B. For the same reasoning, this angle here is 180 minus B over again AX. Alright, and now if we just divide these guys, so we have CAX first actually, of course here we applied it on ACX. If we just do that, if we divide, like just try to divide them, AX will cancel, BX will, and CX will cancel as well. So we just have sine B over sine C. So sine B here over sine C. But guess what? Like we already know that this is 1, because we know that AB over AC is just sine C over sine B. It's literally the law of sines in the original triangle. So yes, we're done. So that means just that M prime is the midpoint. So AM prime is median. And we're done. So M prime is M. Alright, so that was a very nice way to construct the Symmedian. Now we want to dive into like more details and more nice properties regarding the configuration. Alright, so now with the properties of the Symmedian, as you can see we have tons of properties, and proving them can be like a little challenging, but we'll see that actually each one of them, like proving it is not really that difficult, and hopefully like we'll find a way like to keep track of all of them so that you remember them if you want to prove them during a contest. Alright, so first of all let's have a look at our diagram. It's very simple. We just have a simple triangle ABC, and we have just the circle, and just like the way that we constructed the Symmedian. So we intersect these guys at X, and immediately we know that AX is a Symmedian. By the way, like always keep that in mind. This will always appear, like in many problems. You have these two intersecting and you have this point. So it's very nice to immediately catch that AX is a Symmedian. And because you're comfortable with the Symmedian, so you can get many nice stuff. Anyway, we'll just like right now intersect the Symmedian with the circle and with the point here, D. Like at D and at K. And M, of course, we know is the midpoint, and we know already that we have this isogonality here. So, alright, we have some stuff that we already know. So, let's have a look at the properties. What are they telling us? So, property A, KA is a K-Symmedian of triangle KBC. Alright, so if you look at the triangle KBC, this triangle, they're telling you that, guess what? The same line, this line like AK, which was the Symmedian in this triangle ABC, it's also a Symmedian in this triangle BKC, which is like really nice. Like kind of a duality here. Symmedian of this triangle, also Symmedian of this triangle. But how can you show that? How can you show that it's the same? Well, you have many ideas here. You might say that, okay, we'll just use the definition. That means we just to show that this is the like the Symmedian, then we just need to join Km and show that this angle equals this angle. That's one possible way to try it. However, remember that we already found a way to construct the Symmedian using what? Using tangency, right? Like the two tangents. And guess what? You literally have the two tangents lying right here. So that's why we just really can consider the constructing of the Symmedian idea here. How do we construct the Symmedian? Remember the steps. First of all, you have your triangle, you draw its circumcircle, you take the tangent, so that's the first tangent here, the other tangent here, you intersect them, and guess what? You just get Kx is the Symmedian. But wait a minute, Kx is just Ka. So that's it, we're done actually. So that's very nice. Just from the previous one, we just got it. So right now I just want to reference each one and write a short proof. So you just like from constructing the Symmedian lemma, of course applied on triangle BKC. Yeah, this should remind you immediately what to do. Alright, now the other one. What do you also know? Okay, the other property is triangle ABK and AMC are directly similar. So we have some nice similarity. Let's have a look. ABK, so that's this one here, ABK, and AMC. These two. Let's see. Do we have some angles that we know they have in common? Well, of course we do. We have, first of all, this angle here is equal to this angle. Nice. Do we have other angles? If you look at it, do we have these two are equal? Of course we have, because these are isogonals, right? So yeah, actually that's enough already. So let's just quickly sketch the proof. So you can just say that BAK equals MAC. We also know that BKA equals MCA. Of course, the first two I want like couple just like from the isogonality. This one here like having the same arc. So just like by AA we're done. Like we have two angles, so we get the third. Alright. Next property. Before we discuss next property, actually look at this one. Take some time to appreciate it. If you know these two like are similar, then you have, first of all, this angle is equal to this, and this is very nice because handling this angle usually is not very simple, very like good actually. Remember, like dealing with angles with the medians, usually it's not very nice because unlike the orthocenter, circumcenter, incenter, we don't really know the exact angles, right? But usually if you want to deal with angles in the median, then either you're going to pick the signs, like to go trigonometry, because you can apply ratio lemma and you have nice properties, or if you have like maybe the symmedian, then you have tons of nice properties as well. So let's keep that in mind. Another thing to get from this similarity is that imagine in some question they're asking you to maybe evaluate some lengths, like maybe BK or AK. Because of the similarity right now, you can just map these into the triangle AMC, which is super nice. So yeah, this similarity is very helpful. Now let's move on. Like C, they are telling us we have BD over DC is equal to AB over AC, like all squared. So this one here, BD over DC is equal to AB over AC all squared. And this one you should actually immediately cache the proof here, because you already proved it. This one we already introduced in the isogonality, right? The isogonality, like ratios. If you remember, we proved it here, right here. We said that BD over DC times BE over EC is equal to AB over AC all squared. But guess what? Here in our like configuration, one of them is the midpoint, so it will just vanish, and hence we just have this is equal to this, which is super nice, because that means now you know exactly where is the symmedian. Like you know this, remember, like this is actually like BD over DC. This proportion is fixed, like it defines the point. So that means we literally knows like we literally know where exactly is the symmedian, where does it meet the side. So that's very useful and helpful. Keep it in mind. You can check whether a line is the symmedian or not if you just like know. For example, if I just give you the side, let's say like 2, 3, then you know that this over this is just going to be 2 over 3 all squared, so 4 over 9. So that's very useful. Okay. Of course, again, like a quick sketch of the proof, I can just say maybe BD over DC times BM over MC is equal to AB over AC all squared. Of course, if you're asking where did we get this from, then just isogonal ratios. Okay, so we're done with that. Let's move on. What do we have? We have now this one. So they're telling us AB over BK is equal to AC over CK. AB over BK equals AC over CK. Okay, I want to like rearrange this. I want to say AB over AC is equal to BK over CK. Makes more sense in this way, because if you try to focus here, then you'll immediately cache the proof for this one. Why do we have this over this is equal to this over this? It actually just comes from the previous thing that we just mentioned, just from here. It literally follows. How exactly? Because we know AB over AC all squared is equal to this part BD over DC. But remember, we can also say the same thing about here. We know that BK over KC all squared is also equal to BD over DC. And why, you're asking? Well, because we know from A that KA is also a symmedian in KBC. So we have literally the same thing. And guess what? That means BD over DC is equal to both of them squared. So that means they are equal. So that's simple actually. We just need to combine part A with part C. So I'll just actually have like a quick sketch here, I will just say that like AB over AC squared is equal to BD over DC, which is also equal to KB over KC all squared. Of course, this like just came from mixing part A with part C. Yeah, that's it. By the way, this actually, if you just rearrange, like get rid of the ratios, like you can just say that AB times CK is equal to AC times BK. So you can just rearrange this one. AB times CK equals AC times BK. So just like this will help you memorize it in an easier way. Just like the product of the opposite sides is equal. And we'll see later that this actually a quadrilateral ABKC, we call it's something special. We call it a harmonic quadrilateral. A harmonic quadrilateral. We'll see that later, and we'll be dealing this in the in another chapter actually. I think chapter 8, like the harmonic quadrilaterals or the projective geometry. Yeah, this will be like very, very nice. But anyway, we'll discuss that later. For now, we can just move on now to property E. So property E is just telling us the circle BCX, this one here, this circle, just, oops. Yeah, this circle, they're telling us that it meets AK, the symmedian, or like the chord AK, at its midpoint. So this thing here is just the midpoint of it. So that's it. How exactly can we prove something like this? We have a midpoint here. Okay. So first of all, of course, we have this circle. If you try to look at this circle, BCX, this is, by the way, like an isosceles triangle because XB equals XC. And we want to show that it hits this one at the midpoint of the chord. This actually should remind you of doing something here. Remember, whenever you have a chord and you have a midpoint of a chord, then this should remind you to construct one very nice point that has some relations to the midpoint of a chord. And that is the center of the circle, right? If you just take the center of the circle, O, the circumcenter basically, then we know that ON is perpendicular to AK. That's nice. And the nicer thing about it is, remember we have some tangents, then we also, if you connect OB, then we have a perpendicularity, and OC as well. So definitely we should consider this. So that means if you just bring O, you bring like O, maybe somewhere here, this one we already know it's 90, and this one is 90, and this one is 90. But guess what? If these are 90s, then we already know that O itself lies on the circle BCX, right? In fact, we know exactly what is the what's the diameter. It is just OX. So OX is the diameter of this circle because everything is a 90. And guess what? Because ON is also like 90, ONX, then that means N as well lies on this circle with diameter OX, and hence we're just done with the proof. So yeah, literally like to prove this one, you just need to notice that you have a midpoint of a chord, so just define O. So just like define O, and of course define N, like as we said, like the midpoint of a, what was it, AD I think, no, AK. And now like you'll be basically just done, or we can just say actually OX is the diameter of the circle there mentioned, BXC, and we know that ON is perpendicular over AK. So that's actually is enough. Hence, like N lies on BXC. Alright. Nice. So let's just erase this one here. Okay, what next? Now let's move on to part F. So property F, they're telling us that BC is actually the B symmedian of BAK. BC is the symmedian of this triangle. And also, like in the symmetry of it, we also know that BC is the symmedian of this one. Makes sense. If we can show one, then definitely we can show the other. So as you can see, we have tons of dualities here. Like this was a symmedian, AK is the symmedian of this triangle and this triangle, but also BC is also the symmedian of this triangle and this triangle, which is super nice. But anyway, how can you prove that? How can you show that BC is the symmedian there? If you want to go to the definition, then that means you need to take the midpoint of AK. Like that means you want us to show that this one here is equal to this one here. And actually you might try that, especially that we just showed that this point lies on the circle. However, we want to introduce a much easier way, in my opinion. What exactly is this way? Okay, we're going to use a previous property that we already proved, property D. Why exactly? Because this property, if you think about it, it lets you know exactly where is the symmedian just using the circle, right? So if you already have the harmonic quadrilateral, which we just defined previously, what was a harmonic quadrilateral, then you already know, if you just have one point on the circle, we know exactly where does the symmedian hit the circle, right? So just like you know that if you have a triangle ABC, and you want to know where does the symmedian hit the side BC, like at D, then you just check this one here. You just check this one here. Then we also know, like point K is the only point that satisfies property D. So that means if I have just a triangle ABC and I have a point here on the circle and I want to know whether this one is on the symmedian or not, I can just check this one. So that means now in this triangle here, if I want to know whether this thing is a symmedian, I just need to check whether C lies on the symmedian, and hence I just need to check whether this works. Of course, I just need to replace it. So for example, I just need to show that BA over BK equals AC over CK. But guess what? It's literally the same as this, but you just need to rearrange it. And remember, like we said, if you just cross multiply, then you just get the product of the opposite sides is equal. And of course we already know that because it's a harmonic, right? So we already have this, that this times this is equal to this times this, just from here. So yeah, so that means we exactly know that C satisfies this relation, and hence it is the lies on the symmedian. Okay, one question you might ask is, wait a minute, maybe we have other points also that satisfy the same. Maybe also this one satisfies, and maybe we have a third point, right? So we need to prove that there is a unique point that satisfies this. In fact, we want to prove a more general result. It's very, very obvious actually result, but let's just prove it here. If you have something like this, and you have 2 points, let's say, on the arc, if we can show just that, if we can just show that this over this is unique to this point, meaning that if this is also equal to this over this, then they must be the same point. So let's just prove that. So let's say x1 and x2. If you think about it, let's assume the contrary, that guess what, we have bx1 over x1c is equal to bx2 over x2c. Then what can we say? Well, because they have the same arc, then these angles are equal, and from here, from SA we get SAS, So we get that the two triangles are similar, and if they are similar, then guess what? That means this angle BCX1 is equal to BCX2, which is a contradiction, like unless they are equal or they are the same point. So yeah, that's just like for you to make sure that yes, we don't have many points that satisfy this, only one, only unique. So that means just right now we can just say reference D, property D, and that's enough to prove F. So that's from D. So to prove F, just use property D by just rearranging like the one. So CA over CK equals PA to BK. So property D is enough. And remember, like, to show just like it's a unique point. And the proof is really like obvious. Alright, now finally the last property here in the diagram. So we have property G. Property G, BC is the interior angle bisector of AMK. Let's have a look. AMK, let's draw it. This one here. So we have BM, this thing here is the angle bisector of this. So these two angles are equal. And they are telling you that MX is the exterior angle bisector, MX, which is this one here. So we need to show internal angle bisector and external angle bisector. But guess what? We already know that the interior and the external angle bisectors are always perpendicular. And yes, they are perpendicular here, because like X like lies on the perpendicular bisector, since this is isosceles. So of course XM is the perpendicular bisector. So actually no need to show MX is an external angle bisector. It's enough just to show this one, and the other one follows directly, because like we just know MX is perpendicular, so that is actually the external angle bisector. So alright, let's just show that these two angles are equal. How can we show that? Angle AMB equals angle BMK. Okay, what do we want to do here? We want to do something very nice. Remember, like the previous stuff that we got, we had some similar triangles. We had actually this angle here is equal to this angle here. So probably instead of working with these, we should just work with their supplementary, right? So what do we want to do? Instead of showing this is equal to this, we want to show like the other ones, like this equals to this. And now we can manipulate this one, we can take it to this one. So right now our goal is just to show that like this is equal to this, right? These two are equal. Okay, what can we do? So just let me write it. Right now let's focus here, proving these two are equal. Well, this one here, we want to like get it to that angle, but this one is actually an exterior angle to this triangle BMK, and hence it's equal to the sum of the other two angles. So it is equal to this angle plus this angle. So we got this part. So right now that means we just need to show that this angle here, which is B, equals to this angle. So our goal is just to show that this angle is B actually. Okay, how can we show this angle is B? To show BKM is B, can we play with this angle? Well, remember, you have isogonalities, right? You have a symmedian and you have a midpoint, so you can play with the isogonality. So yeah, definitely. This one here is just, we can manipulate it to this one because of the isogonality again. And guess what? This one is already B because it has the same arc as this. So yeah, we're done. So let's just quickly sketch a proof here. Our goal is to show AMB equals BMK, right? That was our goal. So we can just actually deal with the other ones, exteriors, as we said. So we can just say that we can start with something like this. BMA is equal to 180 minus AMC, which is equal to 180 minus, and remember AMC we can just map it to ABK from this similarity, and then ABK we can just say it's 180 minus ABK. We can take it into two parts, like to ABC plus CBK. Then we can take this like ABC. Remember, we can replace it with AKC plus CBK. We can keep it. Okay, but now we can take AKC, this one here, as we said, AKC is just equal to BKM using the isogonality of the Symmedian and the median. So that means we can of course keep CBK, but now BKM plus CBK, you can easily see, just throw this one here, that they're just their sum is just 180 minus this one. Or actually sorry, yeah, we can just say that it's BMK and we're done. Yeah, that's it. Of course, each one of these came from one bit of the previous ones, the previous properties. So yeah, you should just keep track of each one. Where did it come from? Alright, so yeah, that's it. That was our final one. And of course, as we said, showing mx is the external angle bisector. It just comes from the fact that it's perpendicular. So if you want, you can just add that mx is perpendicular to BC. So that's actually also enough. So yeah, right now we have proven all the previous properties. Again, you really need to keep these in mind. We just know that whenever you have this diagram, which will appear a lot in your Math Olympiad journey, then you can just say that this Symmedian here is not only for ABC but also for this one, and BC is actually also the Symmedian of this triangle and this triangle. That's one thing. Another thing to say is that if you have this point as D, then you know this ratio. And if you know K, then also you have a ratio, the harmonic ratio that we said. Like if you multiply these, it's the same as these. So you can keep that in mind as well. And we also have this nice similarity between this one here and this one here. Nice. And you also know that the circle BCX bisects the chord, right? Bisects the chord, as we said, of the median, of the Symmedian. And finally, you have this nice angle bisector property. So yeah, these are all the properties that we discussed here. And now we'll move on to another diagram, another configuration. Alright, so our configuration right now is circles inscribed in segments. What exactly is that? Let's have a look at our diagram immediately. As you can see, we just have two circles, like the big one and the smaller one, and they are tangents. So the idea is actually we have this big circle and we have just some chord AB, and we want to take a circle that is inside this segment. Like this thing here is called a segment actually. So we want this to be inside it such that it's tangent to the circle at T and to the chord at K. And whenever you have this diagram, then you have something very nice, which is if you just take TK and extend it till it hits the circle, it's going to hit it at the midpoint of the arc. So this M is actually the midpoint of the arc. Yeah, that's exactly what we want to prove right now. So it's just like the midpoint of the arc. And of course, if it's the midpoint of the arc, then we know that MA equals MB. So yeah, let's give it a try. How can we prove that? So right now our goal is just to show TK, like it hits it at M. We want to show that this one is the midpoint of the arc. So what can we try to do? So here actually a very interesting idea, a very common idea to do whenever you have two circles tangent to each other is to actually consider a homothency centered at the tangency point that maps this circle into the bigger one. You always have such a tangent, such homothency, sorry, because like this point is going to stay the same. This is going to be sent to this one. You can define it in this way. and that means that this circle will be mapped into another circle that has center O and passes through T. So guess what? It's exactly like the bigger one. So yeah, we do have such a homotety. So let's just consider this homotety. So if we consider this homotety, what will happen? Actually, let's immediately try to sketch the proof. So we just like consider the homotety like H such that like it's centered at C, mapping. Let's just name the circles just to make life easier for us. I'm going to name this omega and this as gamma. So mapping omega to gamma. So now what do we know? We know that this homotety maps point P to O, like the centers. But it also maps K to M. By the way, we don't know that M is the midpoint. We just know that it's like the intersection, okay? So of course, the point K will go to the, like the other circle. So it's M. So the image of K, it's just M. Very nice. But if you look at it right now, that means of course that OM, if you draw OM and PK, clearly PK is perpendicular to like AB. So that means that we already know that OM is parallel to PK. Why is that? From the homotety, right? Like OM is parallel to PK, because as you know in homotety, like when you send a segment to a new segment, then it's going to be parallel to it. That's exactly what happened here. This is like the new one, OM, this one the original one, PK. So we have the parallelity, very nice. However, we already have a perpendicularity. We know that PK is perpendicular to AB, as we said. We already have this perpendicularity right here from the tangency. So that means we also have a perpendicularity here. So that means that if you join this one here, it's going to be perpendicular. And you already know that if you take O and drop a perpendicular to any chord, then it's going to be bisecting it. And hence M lies on the perpendicular bisector, and hence M is the midpoint of the arc. So yeah, that's it. So we get OM is perpendicular to AB, which just finished the proof. So we got that M is the midpoint of the arc. Very nice. And of course, as they said, like here, MA square equals MB square, of course, because they are equal. But they added something nice, which is, it is the power of point M with respect to omega, this one here. So they are telling us that, still delete these, MB square equals MA square, which we already know, but it's also equal to the power of point M with respect to this circle. And of course, we already know that this is actually equals to MK times MT. And hence we just need to show that MB square equals MK times MT. Guess what? This one, you should immediately spot what does this mean. If you have this square is equal to this times this, then you have a tangency, right? Tangency to this circle, the smaller one here. This, you need to show that it's tangent. And if you need to show that it's tangent, then that just means you need to show that this angle is just equal to this one. So are they equal? What do you think? Of course they are, because this one here is just corresponding to this arc, and this one is corresponding to this arc. But guess what? The two arcs are equal. So yeah, that's it. That's correct. So just like for the second part, like we can just say, this was just the first part. The second part, you can just say that MBK equals MTB. MBK, as we said, this one is equal to this one. And why is that? Just like from 1. So that just means that MB is tangent to MBT. And as we said, from the tangency, we just get that MB square is equal to MK times MT, which is indeed the power of point. Very nice. So we have these two to keep in mind. Remember that M is the midpoint of the arc. So if we have just some triangle here, You remember that we used to call this the golden point, right? Because it has too many properties, and it's also like the circumcenter of AB and the incenter I, ABI. Anyway, right now that's everything to to cover in this particular lemma. Now we can move on to the next diagram. Alright, so now we're still working with the same configuration, but we added additional stuff. So as you can see here, we still have like the big circle, the two circles, and we still have AB, and we still have that if we join this, you get the midpoint of the arc. We already know this right now. But what did we add? We just added this. We added an additional tangent from C, an additional tangent from just a random point here. So this tangent is just CD, tangent at L. And now what do we want to do? Now we want to show that, guess what, the incenter of ABC, the incenter is actually the intersection of CM and LK. Now of course showing it's on CM is a piece of cake, because like M is the midpoint, right, of the arc. So of course CM is the angle bisector, so I lies on it. However, the real deal is to show it lies on LK. So that's what we want to do. So we want to define this intersection, and we want to show that I is, guess what, the incenter. Okay, so how can we do that? Alright, right now, if you just look at the diagram, then you have some stuff that are very nice. You have the incenter I, A, you have B, you have the midpoint of the arc. So, remember the golden point. We know that M is the incenter, the circumcenter of AIB, remember? So that means we just need to show that MA equals MI equals MB. We already know, of course, MA equals MB. So if we can show that MI equals one of these, then we're done. But guess what? From the previous theorem, or the previous lemma that we just discussed, we already know that MB square is equal to MK times MT. So that means if we can show that MI square equals MK times MT, then we'll be done as well. So that sounds like that looks promising. So let's give it a try. So right now, if we can just show that this times this is equal to MI square, then we'll be done. Of course, whenever you have something like this, then you can turn this into tangency condition or angles condition. That will be even more beautiful. So to show MI square equals MK times MT, then that just means that you need to show that MI is the tangent to this circle, right? To this circle. This one like this. And of course, that just means that you need to show that this angle here is equal to this angle. If we can show this, then we'll be done. Alright, how can you do that? First of all, you can map this one into this one here, just from the opposite stuff. Actually, let's just connect this dotted line. Yeah, let's actually draw this one as well here, and this one here. Okay, so right now, if we can just show that this one here is equal to this one, then we'll be done, like this. However, how can we do that? Well, actually, what we want to do right now, it's not very easy to do this actually, but what we want to do is, we want to show that this thing here is cyclic. This quadrilateral is cyclic. CTIL. Now what's the point in showing it's cyclic? It will be very nice because the angle, this one, we can manipulate it now. We can go here. It's actually equal to this. And if this, right now, that means we just need to show these two are equal. And hence now, if you think about it, it's just like showing like TL and TI are isogonals, kind of, in this triangle, CTK, right? Something like that. So instead of showing these two are equal, we can, for example, show that this is equal to, to this, right? And of course, like if we want to show these two are equal, then if you look at this one here, like the big one, then it's just corresponding to this arc LK, so it's equal to this one here, right? Because it's like a tangency here. It's also have the same arc, like same segment. But guess what? This one is already equal to this from the cyclic quad. Like this is exterior, so it's equal to this big one. So yeah, so that means if we can just show it's cyclic, then we'll be done. So let's focus on showing it cyclic. How can we show this is cyclic actually? And don't worry, we'll be writing the proof in details later. But right now let's just focus on showing it cyclic. How can we do that? Okay, so to show that this one is cyclic, of course, you know, we have many options, many angles to choose. But what we want to choose here is we want to choose angles that are corresponding to some arcs so that we can play with them. So, for example, what we can choose maybe proving this one is equal to that one. And why did I pick these? Of course, you can try others, but I picked these for a reason. Because this one here is, guess what? It's the same as this arc, right? This arc here, TK. And this one actually is also the arc, the big one. So if I just can show that these two have the same measurement, then we'll be done. Now think about it. It's actually easy to show that. Indeed, they are equal because we can just consider homotopy T. So our same homotopy that we discussed before that maps the small circle to the big circle. Clearly, it maps this arc to the bigger arc. And hence, they have the same measurement, right? So yeah, that's it. So that means that indeed, from this homotopy, the two angles are equal, and hence we got our cyclic quad. So let's actually write that. So to prove that I is the incenter, we need to define to prove many claims first. This one is not very easy, unfortunately. So you need to make sure when you memorize it, like you memorize the key ideas. So the first idea is show that this thing is cyclic. To show this is cyclic, as we said, the details is just like take homotopy from homotopy that we said. We just know that TLK is equal to TCM, and that's it, just to show this cyclic. Of course, like the reasoning is just the arc TK would be mapped into the arc TM in the other circle. Okay, now our second claim is just to show that once we're done with this, let's delete it. Yeah, our second claim is to show that this angle, as we said, is equal to this one here, right? So that we have the tangency, and we can say mi square equals mk times mt. So our second claim is just show that mik equals mti. And to show this, you can just do some angle tracing, as we said. So first of all, you can say mik equals this one here. So you can just say mik is just CIL, but CIL from the cyclic, it's equal to this, so we can move it to CTL. Nice. So now we just want to show these are equal, and as we said, to show these two are equal, you can just do this nice manipulation. You can move them to showing these two are equal. So now to show these two are equal, we can just say that CTI first. You can say but CTI is equal to the exterior angle. Remember, like this one here, it's just equal to the exterior angle, this one. So it's actually equal to KID. But KID is just equal to this arc to this arc. So we can just move it immediately to this arc. I mean to this angle, KTL. Alright, so that means that CTI equals KTL, and we have this kind of isogonality now, so that means you can just say that once you have this isogonality, then you can say the blue ones are equal. So CTL is same as KTI. CTL equals KTI, and yeah, that's it. So our claim is done, and because our claim is done, then that means we can just immediately say mi square equals mk times mt. Just done with this claim. So mi square equals mk times mt, which is equal to mb square equals to ma square, and hence like m is the circumcenter, like of a, b, I, and hence I is the incenter. Okay, we're done. Alright, our final configuration in this lesson is the Mixtilinear Incircles. What exactly are these? So if you look at the diagram here, we have a triangle ABC simply, and you have the circumcircle, and you have this magical circle. Look at it. It's tangent to the circle at T, and the two sides at like AC and at L and K. So it's kind of an incircle, like it's tangent to this, but not to BC, instead to the arc BC instead. And hence the name Mixtilinear Incircle. Okay, so this actually has many nice properties, and most of the properties just come from the previous two lemmas that we discussed. In fact, right now I strongly recommend that you just go there and apply everything that we got before from this actually, and from like this to the same diagram, and that's exactly what we'll be doing right here. So from the previous actual lemma, we already concluded that I, the incenter, should lie on this chord, right? KL. Look here, we said that I should lies on the chord KL. By the way, it's exactly the same diagram, but now it's like this chord CD, it's CA. Like this circle is a bit bigger, so that CD coincides on like a CA. So we can, like, we don't want to prove again that I lies on LK. We just can conclude that from the previous. So we know that I lies on KL, but where exactly? If you think about it, right now we have this thing is an isosceles triangle, of course, and hence we know that AI, the angle bisector, is also a perpendicular bisector, and hence I is the midpoint of KL. And this is exactly what the first like part A of the like lemma here tells us. So let's just sketch a proof for this. So the proof is just from the previous lemma. Previous lemma just tells us that I lies on LK, and now we know that AL equals AK, hence AI is like a median, and that's it. That finishes it. Okay, nice. So we know that I is the midpoint of KL. What else do we know? Also from the previous like lemma, specifically the proof that we did, we showed part F. We showed that BKIT was cyclic. Remember, BKIT was cyclic. We showed that this thing here is cyclic. So you can just repeat the same proof there. Look, we showed that in one of the lemmas. We showed that CTIL was cyclic, and here you can literally do the same thing. Hence, no need to prove that again. Again, just try to make sure that you understand how is that happening. Like this is cyclic. Just try to like get the sense that this is just the same, or let's say a special case of the previous lemma, and hence part F is also proven. So let me just add some pages. Or actually, let's just move on to this diagram, which is better. As you can see here, it's already clear that these are like cyclic. BKIT is cyclic and TILC is cyclic. And as we said, the proof just comes from the previous work. So I can just say here, F comes like from the previous proof. Previous lemma proof. And it was just some simple angles. Okay, so that's for part F. What do we also have? Actually, let me delete this now. Okay, what do we also know? We know actually, part B is, yes, we have this nice thing. Look, TL passes through the midpoint of the arc. And that's actually really obvious. Why? It comes from the lemma before the previous one. If you remember, we said that if we just have like a circle inside a segment, and this is basically the segment here, this is the segment just between the line AC and between this arc, then this circle, actually you just take TL, it will hit at the midpoint, right? So that means we already know that MB is the midpoint of the arc, and similarly MC is the midpoint of the arc. Also same idea, TK just hits it at the midpoint. So very nice. So right now we got two midpoints as well. Okay, what do we also have? In fact, you can like clearly see that these two are parallel. Why are they parallel? How can you prove that? Well, guess what? You can also do like the same idea that we did before. You can take a homothéty that maps like centered at T, that maps the small circle to the bigger circle. Hence, it will map L to MB and K to MC. And hence, we have the parallelity, which is super nice. Okay, so right now we have all of those. Actually, let's just sketch the proof for part B. They're already like obvious. They all come from the previous configurations, and that's why we discussed the previous configurations as well. So B just comes from like what was the name of the lemma? I think circle side like a segment lemma, whatever. Okay, what do we also have properties? Yeah, we have that TI passes through the midpoint. Now this is something very, very nice. If you look at it, we have TI will pass through the midpoint of the whole, like the big arc BC. So the big arc BC, point S is the midpoint of it. We know that TIS are collinear. This is something very nice, because you like from here, you kind of have a way to construct point T. If you think about it, what's this point T? How can I construct the Mixtilinear Incircle? One nice idea is you can just take the midpoint of the arc. You have point I, just connect T, SI, you will get this T. So this is a very nice way to construct T, right? And why is that true? Actually, it's just simple angle tracing. You just need to angle trace. Remember, you have tons of cyclic quads here. So for example, you can just say here, you can just go for this angle maybe. Our goal is to get this arc. If we get this arc, it's half of the big arc BC, then we'll be done. But guess what? This angle here, which is like corresponding to that arc, is just equal to this. And we already know what's this angle. It's just 90 minus A over 2, right? Because these two are equal, like 90 minus A over 2. And that's A here, isosceles triangle. So yeah, so we just got that this one is 90 minus A over 2. And hence, indeed, it is the half of it, right? Because this is 90 minus A over 2, this is 90 minus A over 2. And of course, 90 minus A over 2 is just B plus C over 2. So yeah, very simple to show that. Let's just sketch a quick proof here. To prove C, we just say that CTS is equal to ALK from the cyclic, which is equal to like whatever 90 minus A over 2, or you can just say B plus C over 2, and that's it. Very nice. So we have all of these nice stuff. Do you have other properties? Okay, we're done with A, B, C, and F. So now we just have D and E remaining. Okay, like right now we'll consider also another diagram. So here, what exactly are these properties? Again, these properties are aimed just to locate point T, because this point T might appear in some problems and you have no idea how to deal with it, like the mixtilinear tangency point. So right now we just want to have as many properties as possible, so that when you have this configuration, you're very comfortable with it. Before, remember, we just said that we have this nice collinearity. You just take SI and hits it, like let it hit the circle, it will be T. There are other nice ideas, very nice properties, which are, guess what, if you take the touch point of the incircle, which is D, and also the touch point of the X circle, which is E. So here, like, imagine just that you have an X circle and its tangent at E, like this. Then guess what? We have very nice stuff. First of all, we have the line AT and line AE are isogonals. So that just gives you another way to construct point T. Just draw AE and take the isogonal line and let it hit the circle. That's very sweet. Another thing is actually line TA and line TD are isogonals, but in this triangle. So you also have this one here is just equal to this one here. Okay. Now you might be wondering about the proof. The proof for this fact here is going to be done in the inversion chapter. So we'll leave it to that chapter, chapter 8. However, like if we assume that this one is correct, then we can prove that this one is correct. So right now let's just show that we have this isogonality here, assuming we have this one here. And again, if you want, like, just go to chapter like chapter 8, like in the like one of the exercises, it will be one of the problems. Let me check. Yeah, it's problem 8.31. It's an EGMO problem, 2013, problem 5. I will leave it here for you. So that will be property what? Let me check. That's property D. Yes, property D. So in the inversion, if you like familiar with inversion, just try it out. Okay, now for property E, we can do a proof actually. Okay, so now assume that these two are equal, and our goal is to do this. First of all, what do we want to do? Since these two are equal, we want to use this fact, right? So in order to do that, this is like very common, just like extend this. Why are we extending it? Because we want to have this arc equals this arc, which gives you something nice. So let's just define this point. Let's call it T prime. Why did I call it T prime? Because like we have this nice thing here. These are equal, right? In fact, you can say we have like a symmetry over the perpendicular bisector, right? Very nice. So now if you just consider a reflection maybe over the perpendicular bisector, or actually before we just do this, let me just join this thing here. If I join BT prime, we already know that this one here is equal to this one here, just because they have the same arc BA. So now we just want to show that this angle equals this angle. And now here comes the nice just reflection over the perpendicular bisector. If you just consider the perpendicular bisector, then the reflection will like E will go to D, C will go to B, and T prime will go to T. We have all of these. So that means that, look at this angle CTD. Let's have a look. CTD. It will go to what? C will go to B, T will go to T prime, and D will go to E. And that means that they are equal, the blue one and this one, and hence we're done. So yeah, so just consider a reflection, like to E, just consider a reflection over perpendicular bisector of BC. And yeah, that's it, we'll be done. Again, as I told you, we assume D. Be careful, E depends on D. Alright, so as a summary, today we learned many assorted configurations that are useful, pretty useful, and they, like, you need to make sure to have them all in your mind, so that when you're facing some geometry problem and you notice this some configuration that's similar to ours in Alright, so as a summary, in this video we discussed many important assorted configurations. Each one of these will appear in many geometry problems, and you'll really have to remember these, keep them in your mind, and of course solve as many problems from the exercises as you can, so that you know how to apply them basically. And of course, as I told you, you cannot really reference all of those immediately. It's preferable that you prove them, and that's why we try to organize this lesson by providing just a sketch of the proof for each idea for you to be able to make it as a reference. I'll be uploading this one onto the Discord server, so make sure just to join the Discord server in the the link is in the description. You will find it there, the file, and of course you can always return to the video to in case you forgot how to prove something. Okay, so just a quick recap, we discussed the Simson line. We said that the Simson line bisects pH. This is very important. To prove it, you need to have 3 parallelograms, and each one is built on the previous. Also, we have this nice duality of orthocenters and excenters. So if you just have eccentric triangle, then you also have an orthic triangle, right? Keep that in mind. You can either have it in this diagram or this diagram. And we also discussed the diameter of the incircle. So we have a very nice way to draw X by just taking D, drawing the diameter, and then just hitting it with AE, and you will get it. And also the same idea, if you draw this one here, from X a diameter, then just join it to AX, and you will get D. We also have the midpoint of the altitudes, so we know that DIA and XI, they just conquer at the midpoint of the altitude, which is super useful. We have this nice incircle concurrency, so the diameter of the incircle DI, and we have the chord EF, and the median, they all concur at one point. We have the isogonal and isotomic conjugates, so the isogonal conjugates just they exist, of course, and we have this nice ratio. Isogonal ratios are very important, and the isotomic, of course, exists as well. We define the symmedian to be the isogonal line to the median, and we have the symmedian point, the concurrency of the 3 symmedians, and it is basically the isogonal conjugate of G, the centroid. And we discussed how to construct a symmedian. Just draw the 2 tangents, and just AX is your symmedian. We have tons of properties of the symmedian. We know that if you have a symmedian like this, then we know that the symmedian is the symmedian of ABC and BKC. But also BC is the symmedian of this triangle ABK and ACK. We have some nice ratios. We have BD over DC is equal to AB over AC all squared, and we also have some ratios for the quadrilateral, the cyclic quad, the harmonic quadrilateral. So we know that AB times CK is equal to BK times AC. And we also have that if you draw just this circle, it will bisect the chord, the symmedian chord, AK. We also know that this is an internal angle bisector of this angle, and this one is the external one. So yeah, keep these in mind. And we also have circles inscribed in segments. So if you just have a circle inscribed in a segment, so it's tangent to this and this, then if you just join TK, it will hit the circle at the midpoint. And don't forget that MB square is equal to MK times MT. It's the power of the point. And in this configuration here, Curvilinear Incircle chords, we know that the incenter I lies on LK. And remember, we have this cyclic quad. We have the cyclic quad, CLIT. Very useful. And we have finally the Mixtilinear Incircle. We know that it exists, and we know that I is the midpoint of KL. And we know many stuff regarding the diagram. We know that ML just hits the circle at the midpoint of the chord, of the arc. The same thing as TK. We have these cyclic like quads, this one and the other one. We also have that TI bisects the chord, the arc again, like the big arc BC at S. And we know, of course, we have this parallelity here. KL is parallel to MBMC. And we also have this nice thing. To get T, just get AE and draw the line isogonal to it, and you get T. And we also have another isogonality from the triangle BTC. If you have T and TA, they're isogonals as well. Yeah, so that's it for this lesson. I hope you guys enjoyed this video. Please like, share, and subscribe to my channel, and see you guys in the next video.